Okay, hello. Wow, my mic even works. So this is my first gathering for Gardner, but quite a few people seemed to have recognized me from several completely unrelated areas of activity. So I thought I would start with how might you know me? You might know me from research. I'm the creator of the Mathematica notebook interface. You might know me instead from the 2002 Ig Nobel Prize in Chemistry, which I won for the wooden periodic table. You might know me from my book, The Elements, or Molecules or Reactions, or from the Elements app that came from the Elements book, the iPad app. You might know me from one of the various random iPad apps that the company I founded, Touch Press, made. These things are they're very virtual. You know, I've been in software for a long time. It's all very touchy-feely. You touch it, it spins. It's very cool, and I'm tired of it. I'm done with this virtual reality stuff. All this new, it's new. I want old. So I've decided to become a Luddite, at least provisionally. Back to the land, What am I actually doing? Well, of course, I'm working on a new book because I don't really know how to do anything else, except software, but I'm trying to avoid that. So the new book will be called Things. It'll be out in 2019, and it will be sort of a way things work book, but done in the style of my earlier books with lots of photographs of things. One chapter is how to make a potholder. And in the spirit of Back to the Land, this, of course, starts by me planting a field of cotton last summer. We got lovely cotton flowers. They mature into bowls. At the end of the season, they dry out and puff, poof, cotton. And then we got about 20 pounds of cotton picked by children, as is tradition. And of course, once you have cotton, you need to separate the fibers from the seeds, which is done with a cotton gin. Now, the problem with a lot of machinery like this is that it's very hard to see inside and see what's happening on it. It's opaque, both literally and figuratively. So I made a transparent cotton gin out of acrylic. We actually ginned about 20 pounds of cotton through this gin, and we were able to photograph and see how it all works. So that was nice. Now, steam engines are another example. I love engines, all things oily. And steam engines are particularly difficult. They're much harder than gins to understand because they have a very dynamic sort of motion. And their design, having been refined over centuries, tends to obfuscate some of the most obvious aspects of how they work. So I've tried to make some that make clear. In this case, we're looking at the timing between the valve and the piston. And it turns out that in this design of engine, sort of harmonic motion engine, everything is harmonic. You have, let's say, a sine wave for the piston that's driving the cylinder, and then you have a cosine for the valve. Because what you want is that when the piston comes to rest at the end of its motion as it's reversing, that's when you want the valve to be going as fast as possible to switch the steam over to the other side. So you have this very nice, and this design of engine makes that sort of geometrically obvious that that's how it's working. But all steam engines that have harmonic motion valves use that principle, even ones like this, where it's hard to see, but it's still 90 degrees out of phase. You just can't really see it from the mechanism. Now, I tried to say I'm getting away from, all this virtual stuff. And so these are not animations. These are not computer generated. These are time-lapse photographs of real physical objects, which out there, you can see them if you want. And the physical things are much better than the animations. I just don't have time to show them here. Since this is a mathematical sort of related thing, I thought I should put in a tiny bit more math, because I don't really have much math in this presentation. I showed you the sine and the cosine. The question is, could you make a steam engine that has only one takeoff from the flywheel instead of two? Like, could you synthesize the cosine from the sine by having some kind of mechanical derivative machine? The catch there is that you need to have the one thing in motion when the other one is stationary. So you would need sort of infinite leverage to do that in a clean way. But actually, it turns out, and there are hundreds of patents of how to do valves in steam engines. This is a mechanism that was actually used. And what it's essentially doing is it's taking the very top and bottom of the sine wave, just a little bit, clipping it off, multiplying it by a ratio that's determined by the sort of mechanical leverage of that lever, and then applying a sort of a min and a max function. And what you get is this sort of squared off curve for the valve, which is actually sort of cosine-ish. And in fact, since what you really want is a square wave, it's actually better. Those valves are more efficient because they go faster when they're switching back and forth. So anyway, I originally made these things simply with the intention of photographing them to put them in my book. I was going to make one or two of them, photograph them, and that would be in place of hand-drawn diagrams or what are computer-drawn diagrams. But once I had actually made the physical things, I just liked them so much. They're wonderful. They're fun to play with. So I decided I should actually produce these, and they are available for sale at mechanicalgifs.com.
30 seconds.
And that's exactly where I'm in on my presentation. 30 seconds left. So most toys go for realism. I go for simplicity, clarity of function, stripped down as much as possible, two-dimensional. Some machines have not been able to get two-dimensional. So they're three-dimensional, and they're even harder to understand as pictures. We're really doing this. I have a little micro factory. We have a big laser cutter. We're setting up with production. And you get a kit and go to mechanicalgifs.com, and you can get them. We even have a club, Model of the Month Club. That's 6 minutes.